All right, everybody.
All right, this is the winner here. You got it right. Now listen in calculus.
No.
Okay, so just really quick, before we kind of get into the answer part of it, who here got 96? Gabby, I know TJ did because I was talking to TJ and Bridget. Couple more, cool. So I'll first start off by saying the answer is 96, and that should give you some reassurance for the next thing I'm going to ask. Who would like to present or explain why it's 96? Who's ready to be brave?
I got it by first I got all the outcomes in the noodles, like with all the combinations.
Okay, so what do you mean all the combinations? Did you write it out or did you draw it out? What was your methodology?
I wrote it out.
Okay, let me go to a clean page here. Okay, so you went noodles and then? Are you doing like noodles pork, noodles chicken?
Not shared.
Are you talking about something like this?
Colin Pierce name's not shared.
Oh, yeah, that would explain it. And okay, so something like this.
Yeah.
Okay, and then I assume you kind of add the next level. So what do you add next, or what do you pair next?
So I did like, hang on, let me get back to it. So like I put like, I started with like an N, I started with the NCST, and then I went NCSL, then NCSC, then NCSR, then the NCKT, NCL, NCKC, and NCKR, and I just kept going with that.
Oh, KR. Okay, I'm just gonna put a dot. So you went full exhaustive list, pure brute force mathematics. I like that.
No, I only did noodles and I just multiplied that by.
Oh, okay. So you did all the noodles, and I assume you came up with 32. Okay, and then so you multiply it by 3, and got 96 because there's a rice level that should also be 32, and a tofu level that should also be 32.
Yeah.
I like that. I'm gonna openly admit I like that kind of mathematics, like just jumping in and like brute forcing your way through every single possibility. I think is a brilliant way to approach mathematics. Now, I will say that probably took you a while, right? In terms of like just working out all the different possibilities. I appreciate that. It's definitely going to work, although it probably is going to take a while to make that happen. Okay. Now, anybody else who got 96 as an answer, is that your methodology or did you have a different one?
I had a different one.
All right, what'd you do?
So I looked at the menu and I took 3 times 4 times 2 times 4 since those are the numbers 3 thing, and then I got 96.
Okay, so you kind of took a shortcut, 3 times 4 times 2 times 4. That seems to be like kind of what we did for the coin flip and the dice roll. Like it seems like that's kind of the same problem. Multiplication here could be very well justified. I think we can visually kind of work out why multiplication here is justified. And honestly, I don't think it's any different what Gabby did. So you kind of noticed that there were 4 levels. There was the base level, like the protein level, the veggie level, and then the sauce level. How many choices were there for bases? I think you said there were 3, correct?
Yeah.
Okay, so you could have chosen noodles as a base, you could have chosen tofu as a base, or rice as a base. If you pick noodle, no matter what you pick, how many choices are there for protein?
You repeat that?
Sure. Remind me, how many choices were there for the meats?
4.
Okay, so noodles could actually have 4 different choices, but so could tofu, and so could rice. Okay, well, even at this level, anybody else in the room, how many choices are there right now? Just in the first 2 levels.
Well,
Yeah, I agree, because there are 4 choices for each of 3 different things. 4 here, 4 for the middle, 4 for the end. That's 12 total choices. Right? So 1, 2, 3, 4. Okay, now no matter which you pick at this level, how many vegetable choices are there?
2.
So this could go 2 places, that could go 2 places, 2 places, 2 places. But same is true for the tofu. Oops. And same is true if you choose the rice. So it's 1, 2, 3, 4, 5, 6, 7, 8, 16, 24. Because for each of these 12 choices, you have 2 more. So 12, 2 choices each, that makes 24 total choices. And, this is a brute force thing that Gabrielle did. Gabriella did. But also, let's say the shortcut thing that TJ is taking. Because if there are 2 choices here, or 3 choices here, times 4 choices here, times 2 choices, and then each of the sauces, I can't really even draw this out, but there's going to be 4 choices here more. That's going to be your 96 choices. Right? So this type of thinking is something called permutative thinking, or thinking in terms of something called permutations. And in discrete mathematics, which is the mathematics of counting, which is actually one of the bigger branches of mathematics, this is one of its most basic rules. If you have this multiple choice, taking multiple choices out of a bigger group to create a set, and that set is one of many different sets you can pick, this is the mathematics of telling how many possible outcomes there are. Okay, now I want to help you formalize this before we wrap up today. So can you guys load up these notes? They're not very long. In fact, they're super duper short. But I just want to talk to you guys a little bit about permutations, give you a couple examples, and that will pretty much be our day to day. So about another 10 minutes, max. So please take a couple minutes. It's the same file that I threw in the chat earlier. Okay, I'll put it there again. Okay, I just reloaded into the chat in case you missed it the first time around. But can you please get mathematics? Okay, and so we're going to talk about the other half tomorrow. That's something called a combination. This permutation, I think, is probably the more general idea. Combinations are a specific type of permutation. When you talk about permutations, it's just a way to determine how many total outcomes there could possibly be from a set, or choosing from a set, I should say. But the difference between what we're going to talk about tomorrow and what we're talking about today is that the order matters today. So when you pick first, when you pick second, third, fourth, fifth, whatever, that matters in a permutation, where it doesn't matter in this thing we're going to talk about tomorrow. So a perfect example, when I thought about like what permutations would you encounter just kind of out there in the world, the first thing that popped in mind is a password. All right, so you set a 4-digit password on your phone. If you type in 1234 as your password, that's very different than typing in 4321, even though they're made of the same stuff. And that's the essence of a permutation. You're choosing from the same group, and even if you choose the same 4 elements, when the order matters, it becomes what we call a permutation. In other words, if you pick tofu, chicken, vegetables, and teriyaki sauce, like that unique sequence is a different permutation than if you would pick tofu, salmon, vegetables, and teriyaki sauce. Biologically speaking, we are made the same stuff as pigs. Like we have the same amino acids, we have the same chromosomes, we have the same everything, but it's sequenced in a very particular order that results in us being humans. Whereas for pigs, it's a different sequence, which results in them being a different kind of animal. Okay, more or less. I know I'm playing it fast and loose. And the last thing, of course, when you talk about probability, when you talk about gambling, certainly where the order absolutely matters, whether or not you're going to win $100 or $100,000, the permutations, the number of things that can happen in a certain order, become very important. Okay, and that's the essence of permutative thinking. Okay. Are there any questions up to this point? You guys need me to hold a second before moving on? Where are we in the notes? Give me some feedback. Like thumbs up, we can move on.
Oh yeah, so we're in this thing now.
Okay, I can give you a minute or two. Sure. While Gabby's getting this down, and I don't want to overplay this, but I'm not being fake when I say I think this is probably one of the more important things that you can learn mathematically. So even if you don't go on to be an engineer, so to speak, right, or maybe you're not going to be a physicist or a mathematician, this type of determination, like saying, well, I have 83 things I can choose from, I can only choose 3 of those things, how many different ways can I choose them, becomes the essence of like just problem solving in the real world. I gave you 3 examples here, but there are so many more. In fact, this is a very thing that a lot of people count on you not knowing, and so they can trick you into things. This is a thing that makes something sound like a really good deal, but it honestly isn't. And we'll examine some of those scenarios in the work and stuff. All right. You guys already kind of stumbled on something really important, which is this idea of what I'm going to call the multiplication rule. You're going to see the multiplication rule pop up several times this week because it's very associated with this idea of probability or predicting the percent outcome that something is going to happen, because that's what probability is, just how likely is something going to happen given a random kind of chance. But you're going to find that multiplying is going to be the key to finding outcomes. It has everything to do with the thinking you did so well this morning. If you have 2 choices and then you have 6 choices, for every choice you have 6 things, so 2 times 6 makes 12 total outcomes. If you have 3 bases, 4 meats, 2 veggies, 4 sauces, well, every stage multiplies a number of outcomes. Hence, if you multiply it all together, you're going to get the total number. Now, is it wrong to do what Gabby did? No, absolutely not. You can make an exhaustive list, but certainly if we have something that gives you like 327,000 outcomes, that method's not going to work. It's just going to take too long. Okay. You can always rely on that branching tree diagram, like actually drawing out the number of total outcomes. But again, that tends to be a little more tedious than it's worthwhile. Hence, we can fall back on this general multiplication rule. The total number of outcomes can be found by multiplying how many choices you have for each stage. I'm going to call these buckets, and you're going to see why in a second. Right? And so a direct application of the multiplication rule comes with this example. Right? And so this is your phone example. So like I have like an iPhone here, right? And so I have a 4-digit passcode that I was able to set. So let's say like Miss Simmons wants to break into my phone. Okay? I don't know why, but let's just say she wants to get in it, right? Well, so she has to guess my 4-digit password. And so like a natural question I would ask myself is, well, how likely is she to guess it? Like how many possible passwords are there? Okay? Now again, we could make a branching tree diagram, right? We can say, well, for the first digit, the second digit, the third digit, the fourth digit. For like the first digit, if she's just randomly guessing, how many things can she choose from to enter in that first number? Yeah, so 0 through 9, that gives her 10 choices, right?
Yeah, okay.
Would you say, I didn't catch it? Okay, so she can go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Now for the second choice, how many numbers can she choose from for the second guess? For the second digit? Well, you can choose 0 through 9 for the first digit. Is there any restrictions on the second digit?
Same thing.
I'm sorry, yeah, same thing. I think I heard the same thing. I agree, it's gonna be the same thing. And so you can choose 0 through 9. So if you want to draw like a branching diagram, there's gonna be 10 branches off the first one, 10 branches off the second one, 10 branches, 10 branches, 10 branches, dot, 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 dot. That makes this kind of like a visual representation a little bit tough, but we can think of it kind of in a different way just through multiplication, kind of like TJ was doing. And so what we really have to like identify is how many buckets are there that we have to fill, and then how many choices per bucket. Now, I call them buckets because my professor in college did, because what he was basically saying is there are 4 things that we have to fill up. There are 4 numbers that we have to choose, and so the number of buckets is 4. And as Gabby and others identified, there are 10 choices per bucket. Okay? And so instead of drawing like a diagram or making a big list, we could just use numbers to fill in the digits. And so this is like the first number, this is like the second number, the third number, and the fourth number. And so you can choose 10 digits for the first one. Gabby said, or someone said you can choose 10 for the second. I agree we can do 10 for the third and 10 for the fourth. And for every digit, there are 10 choices. Because we can repeat, and that's an important part of this particular problem. We can repeat, which you start thinking about like what happens if we can't repeat, right? Okay, well, according to the multiplication rule, we just have to multiply these all together because 10 choices, there are 10 choices for that, then 10 choices again, 10 choices again. And we multiply 10 times 10 times 10 times 10, we end up with 10,000. Okay? Which is why, for your phone, a 4-digit password, that would leave 10,000 possibilities for someone to guess to try to break in. So good luck, Miss Simmons. That gives you a 1 in 10. Well, how many times can you do that before it locks out your iPhone? Like 4 times?
I don't know, but you're probably 0000.
It's not. It's not at all. Don't even try that, please. So
Can you spell your name? Mike?
I choose not to comment. So that would give you like what, like a 4 in 10,000 chance of guessing my password, which is why most people get locked out if they just try to do that. Okay? It's also why they invented thumbprints and face recognition, because people lock out themselves on their own phone sometimes. All right. So important question. So like this is like the essence of permitted thinking, right? Like you have like these spaces you have to fill, or buckets as I like to call them. Then you have to determine how many choices you have per bucket. So in this particular case, 10 times 10 times 10 times 10 for a 4-digit passcode, hence 10,000. How do we feel about that?
What was that?
If that makes you feel better.
I didn't quite hear you, Isaiah. What was your comment?
I just learned something new. If that makes you.
It does. I'm glad you're learning something. That's like, that energizes teachers. Hey, could you guys just give me like a thumbs up, like you're following the argument right now? You feel like you can do this and you understand the argument about why there's 10,000 different passwords? Cool. Now the situation is of course going to change, right? And so this happens to be the scenario for this one because there was a 4-digit password and 10 choices per potential digit. So let's flip to the next question. Let's see if you guys can figure out this. Here's a scenario. 30 people enter this raffle, and it's going to give out 3 prizes in this order. We'll first draw out a $100 prize, then a $75 prize, then a $50 prize. Okay, so just 3 prizes in that order. And so how many different outcomes are there for this drawing? Let's take 25 seconds. Let's see if you can set it up. If you get to the answer, that's great. But let's try to set it up. Okay, so what would the multiplication look like in this scenario? Okay, how many different buckets do we need to fill for this problem? In other words, how many spaces are there to fill? In the chat or out loud, how many? Dante, how many? It's not 90. Are you saying that might be the answer? We'll double check on the answer. I just want to know how many spaces, like how many buckets there are for this problem. Dante, how many?
Can you repeat it?
Yeah, so for this problem that's on the board and in your notes, how many different buckets are there? Like how many different spaces do we have to fill for the outcome?
30?
Not 30, nope. For the previous answer, for the previous question, there were 4 buckets because it was a 4-digit passcode. TJ, how many buckets? Not 30. Dante just answered that. I'm looking for how many spaces we have to fill for this problem. Okay, there were 4 for the last one because there's a 4-digit passcode. It's not 30 for this one. It'd be 3, yeah. Isaiah, it'd be 3 because we're giving out 3 prizes. So that would be 3 spaces. Very good. Okay, now, the second question, I think, is where this comes for TJ and Dante. This is their chance to shine on this one. How many things can we put into each bucket? How big is the group that we're choosing from?
30.
30. Okay, so for the first choice, can we agree? That'll be 30 right there. Okay, how much for the second one? Gabby, what do you think? How much for the second bucket? So we choose from 30 people for the first prize, for the $100 prize. How many would we choose from for the $75 prize?
Wait, can you repeat that?
I can, yeah. So for this problem, we're picking 3 winners out of a group of 30. Okay, so for the $100 prize, 30 people are eligible, so the first number is 30. What would be the number for the $75 prize? How many people could win that?
I don't know.
Okay, we can open it up. So spoiler alert, the answer is not 30.
100, would it go down to 29? I need 29.
Why would it be 29, Isaiah? You're absolutely right. Tell me why it's 29.
Would it be 28 since that?
Isaiah, you were killing with the answers, but I didn't hear your explanation. Why would the second number be 29 and the third number be 28? You're 100% correct.
So if 30 people enter for the $100, one of the 30 people are going to get it. So then there will be 29 people left for the remaining votes or whatever. And then after that, the 28 for the 50 since another person already won $75.
Yeah, no, 100%. You were 100% correct on that. And so this is kind of fair warning. You have to think about the situation. In the previous example, we can use the same numbers over and over again. And so it's from the same set of numbers. But here, since let's say me, Miss Marcus, and Miss Simmons were the 3 winners. Well, if Miss Marcus wins $100, she can't win the other one, so she's out of the group. So it's now down to 29 people. You're 100% correct. Then Miss Simmons wins the 75. She's out of it too. I win the 50. Okay, and so you have to watch out for this in this kind of work because you have to determine if you can replace the number or not. Now, the rule still applies here for multiplication. And so we take 30 times 29 times 28. That would make 24,360 possible winning combinations, so to speak, of winners. Winner combinations. There we go.
You know that off the top of your head.
No, I didn't. I got a calculator. I just did it fast off screen.
I was kind of scared.
Yeah, I would be too. I can't do I'm actually really terrible at multiplication in my head. I always have a calculator for that reason. Okay? And so, guys, this is the essence of permanent thinking. And so, are there some tricks along the way? Yeah. You have to know how many different spots you have to fill. You have to know how many can go in each spot. If they get replaced, sometimes the number doesn't change. If they don't get replaced, like this problem, the number does change. Okay, and that's where I want to stop today. We're going to pick this up tomorrow. We're going to talk about a cousin to permutations, which is something called a combination, which is an equally interesting thing. But we've run out of kind of time today for it. In fact, I think I ran about 7 minutes longer than I wanted to, guys. I'm sorry. Anyway, really wonderful job, guys. Isaiah, thank you for showing us like the growth of a thought throughout the day, because like you started really fighting me on the 12, and then you were just killing it at the end. So congratulations, really congratulations to everyone. That was a complicated thing we did today. You guys did awesome. So here's what's going on for the rest of the block. Some of you guys are going to get assigned to rooms. So in just in a moment here, who doesn't need the host today for second block?
Hancock doesn't need it.
Okay, Ms. Simmons, I'm giving it to you first. Okay, so you might get assigned to a room here in a second. It's going to pop up. Just go ahead and go to that breakout room. That's just we want to touch base with you about one or more of your tests. Try to give you an opportunity to pick up some score if needed. If you don't get that pop up, that means you are good to go, and you can just like work on the homework, which I'm going to drop in the chat right now. But also should be in your Schoology too. Oh, I can't do that. I'll drop it in your chat in a minute, okay? Also, if you know in your head you have not finished the test from Friday, that's your priority day. Go take your topic 10 test. We're down to this last week. We have to have time to put in grades, and so we cannot have you guys wait anymore on the topic 10 tests, okay? I'm sorry, Mr. Hancock, we can barely hear you.
Drop me in topic 10.
Okay,
Thank you.
you're welcome.
And then, this is it. You can go now because I messaged you about what you're